Hi, my presentation is on the polymorphism in the Nefilim Dropper. Hi, I'm Mark Embrich. My current day job is as a malware analyst. I wanted to show people an interesting piece of malware. Before the pandemic, I went to DEF CON every year, and every year I came away inspired by the work other people are doing. When you see someone else do it, it doesn't seem so far away, right? So let me stop my video here so I'm not taking up screen space, and let's go on. Okay, so what is polymorphism? Here is the Wikipedia definition. It's polymorphic code that uses a polymorphic engine to mutate while keeping the original algorithm intact. What I'm going to talk about is not exactly that. The malware file doesn't change itself. The dropper uses a function to write a slightly different file each time, such that the file hash is different, but the dropped file functions the same. So let's jump to the end. That's what you want to see, right? I used the dropper to write the payload malware 4 times. It generated 4 different file hashes. We got a bit lucky that VirusTotal knows one of the hashes. And as you can see, VirusTotal lights up like crazy for that malware file. So the threat actors have an interest in changing the file hash such that your anti-malware tools don't know the hash. And we can't talk about this topic without David Bianco's pyramid of pain. There is a reason hash values show up at the bottom of the pyramid. Let's take a look at one way to generate malware payload with different file hashes. Here is the main thing in the function that generates the polymorphism. Don't worry, I don't expect you to understand this at a glance. We'll go into it. The main things to note here are the randomize and R&D functions that are highlighted in yellow. Let's drop into a sidebar. What is the R&D function? In yellow, that's the entirety of a script that I ran to test the functionality of R&D. Note that the randomize statement is commented out. Each time we run R&D in this case, we get a random value between 0 and 1. But without randomize, each time we run R&D, we get the same value. R&D is calculated only once, and the same value is used over and over again. And in this test, I enabled randomize, and we can see that a different random number is generated each time. A few other things to note. The range of values includes 0, but not 1. So greater than or equal to 0 and less than 1. And at least on the host I was testing on, R&D returned 7 decimal places to the right of the period. So now that we understand R&D and randomize, let's go back to the polymorphic code. We can see that randomize is enabled, and we see that R&D is used to generate my return value. Now, I'm looking at the stuff below the dotted line. We can see the code to figure out the range of possible values. If R&D returns a 0, the smallest possible value, we get a 9. If R&D returns 0.9999999, the largest possible value, we return 2. So our range of values is from 2 to 9. Before we move on, take a look at the if statement. We only do the R&D stuff if the value in the array that we're looking at is equal to 999999. So your next question should be, where does 999999 occur in the code? We find that value occurs only in one array and only those 4 times in a row. So let's drop into another sidebar. Now that we know some of the background information, we can figure out how polymorphic is this dropper, meaning how many unique file hashes are possible from this code. We determined that the range of values will be between 2 and 9, so 8 unique values. And we found that we would use R&D only 4 times in the entirety of the code. So we're talking about 8 to the 4th power, which is 4,096 possible unique file hashes. But if you're a math nerd, you might have noticed that only when R&D returns a 0 do we get a 9 value. The next smallest value R&D can return, 0.0000001, returns an 8. meaning returning a 9 is extremely rare. Remember the 7 decimal places? That means 1 in 10 million chances are we going to get a 9 value. So functionally, it's more like 7 possible values to the 4th power, 2,401 possible file hashes. And that's the polymorphism. Hopefully you're thinking, how did we get there? I want more information on what this dropper does. So let's loop back to the start. If you want to follow along or dig into it on your own time, you can find the article on this malware in the Sans diary, where Xavier Mertens discusses the obfuscation of this malware dropper. To find this article, search for Russian dolls VBS obfuscation. And Xavier did us a great favor by uploading the malware sample to Malware Bazaar. So you can retrieve the file from there and go through it on your own. When we first open the VBS, we see a lot of comments. The lines that begin with a single quote and the lines that begin with rem, those are comments with just garbage text. So why would the threat actors do this? I assume that there are some security products that do some analysis on files to guess whether the file is malicious by reading the content and counting words versus programming language, commands, or functions. The point is that this VBS, when you first look at it, has very little content that is clearly malicious. In yellow and green, we see examples of the comments. And the non-highlighted stuff, that's the actual code. It's an array of values, and that's an obfuscation. So first thing we want to do is get rid of the comment lines. grep is a great tool to use here. We can see that we only got rid of 63 lines of code, but it was a lot of garbage. We still have 600 lines of code. Many of those lines are very, very long. So where do we start? If we look at the code, most of it is made up of variables with an array of values assigned to it. But then we have that execute function call. I wonder what that code looks like if I take out the array assignments. We use grep again to separate the array assignments from the rest of the code. Turns out that 556 lines of code are array assignments, and the leftover is 73 lines of other code. Let's take a look at the other code. Ah, man, more comments. And in this case, since it was just a few lines, just those lines had comments, I just manually deleted them. And let's take a look at the other code again. So this is most of the code that was left over. This probably doesn't make sense to anyone, and that's by design. The threat actors don't want you to be able to tell what this code is trying to do at a glance. But what we can see here is that we have a function limpet, and that function gets called a lot. I snipped most of function limpet just to make this more readable, but we'll take a closer look at it right now. Here is the entire code of function limpet. Remember the randomize and R&D we discussed earlier? That's where it's from. So what does this function do? Let's take a look at it line by line. On the left, we have the code from the VBS, and on the right, we have my attempt at recreating that code in a way that's more understandable for myself. So chivalrous and PBL are just constants that are defined. HMX is a value that is passed into the function. KON, blah, 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 is a variable that holds the smallest array address of HMX. So now we know that the values passed into the function are always arrays. OOS, blah, 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 is a variable that holds the largest array address. So on the right side, I call them my array start and my array end. Now, let's take a look at the for loop that follows. Remember that KON and OOS are the start and end of the array. So we're looping through the values of the passed in array. And we saw this if statement earlier. This is where the polymorphism happens. Whenever we find that 999,999 value, we do some math and end up with a random value between 2 and 9. And And if the value is not 999,999, which is the normal case, which is everything else in the arrays except for those 4 times, we do a bit of math, which ends up as just -7, and then we convert that number into an ASCII character. So let's do another sidebar. Let's just take a quick look at the values in the arrays. Note that we see a lot of 7 values and nothing larger than 255 plus 7, 262. This kind of confirms that we're on the right track. So it turns out function limpet is a decoder. It's the thing that converts an array of numbers into text. And here's my pseudocode of what limpet does. You pass in an array of values to the function. It loops through the array. If the value is 999,999, return a random value between 2 and 9. Else, subtract 9 from the value, convert that number into a character, and return the decoded text. Before we go any further, let's try manually decoding some of the values to make sure it works. So the first time we call limpet, we're passing this RSL blah, blah, blah value. The beginning of the array looks like this: 77, 124, 117, etc. So when we do our math on 77, we subtract 7, we get 70. We look up that value on ASCIItable.com. We see that that is a capital F. Then we take the second value, 124, subtract 7, we get 117. Look that up on ASCIItable.com, we get a lowercase u. So far our return value is capital F, lowercase u. And of course you're thinking FU is for function, right? But remember, we have over 500 rows of these arrays. So doing it manually is just way too slow. We want to borrow the threat actor's code, modify it a bit such that we just print the decoded stuff rather than running it. So remember back when I separated the assignments from the code? We can take the file with just the assignments and add our own code with the intent of decoding stuff. So that's what I did. I added my own version of the decoder function, my decoder, and the 2 lines of code below the dotted line to the assignments file and ran it. And here's what that output looks like. We can Control-C in that dialog box to copy the content and paste it into a text editor to take a closer look at it. You may be thinking, but with a little more work, you can decode the whole thing and output it to a text file. Yep, you're correct. I didn't choose to do it that way. I don't have a good excuse. It's just the way it went. Anyway, we got really lucky in that the first thing we looked at is a super important function. So let's take a look at that function. And yep, you guessed it, more comments. So let's do some grep magic to get rid of those comments and take another look. Let's focus on the stuff highlighted in yellow first. See the save to file? That's exactly what it sounds like. That's how you write a file to disk. The stuff in green I found interesting too. It appears the threat actors built in their own debugging type logging. So at the start of this function, it logs fdropped start. This function writes a file to disk, so guessing fdropped means file dropped. So let's take a closer look at that for loop. We're looping through an array made up of a bunch of values. The array is actually more than 500 elements, where each one of those elements is its own array of values. I turned off word wrap so we can actually read the code better. And note that the thing highlighted in green is our old friend function limpet. So we know that we're taking this array of 500 elements where each element is an array, and we're sending each one of those arrays to function limpet to decode. Note that the first element is rum, R-U-M. So let's take a look at that. Okay, so rum is what we expected. It's an array of integer values. And since it's the first thing we're writing, how much do you want to bet that the first 2 values decode to MZ? Let's test it out with the thing we used earlier. And unfortunately, I had a bit of a fail here. So what happened to that dialog box? I mean, we see MZ, but then nothing. My guess is that the values after MZ were not printable characters, so wscript.echo gave me what it could and then failed nicely. Anyway, it's enough for now to see that it starts with MZ. So it's exactly what we're expecting. We're writing a portable executable file. But we want the whole file that gets dropped, right? So like before, we take the threat actor's code, perform the same functions, just make it more readable. Here is the function I added to my previous VBS. Functionally, it's the same as their code. It really is their code. I just changed the path and some variable names. Like the threat actor's code, we're taking the list of 500 plus arrays, sending them to our decoder function, and then writing the decoded stuff to disk. In this case, I'm writing to a file named dropfile1.txt. So here's what dropfile1.txt looks like in a hex editor. We can see the MZ, and it looks like a portable executable file. So I ran it a few more times. Each new file resulted in a different file hash. And as we saw earlier, the first time we ran it, VirusTotal knew the file and it was well detected. But runs 2 through 4, VirusTotal doesn't know these file hashes at all. So if your antivirus is looking for file hashes known bad by VirusTotal, it doesn't know these files. So now you should be asking, well, what about imp hash? VirusTotal does give us the imp hash, but I had trouble searching VirusTotal using the imp hash. I think you need to use a pay-to-comp to do that search. But I was able to take that imp hash value and search for it in Malware Bazaar. Malware Bazaar returned 26 hits, all received between June 2 and June 3 of 2021. The top sample here is the same hash as our dropped file. So I think these 25 other samples are other dropped files with different variations of those 4 random bytes. Let's do another sidebar. Maybe you haven't heard of imp hash. So let's talk about what is an imp hash. Mandiant explains it really well in an article here. The gist of it is that a portable executable file uses Windows APIs for functions like load library, which can be used for process injection or running something. Write file can be used to write a file. When a portable executable, a PE file, makes a Windows API call, we call that an import, as in I'm importing this function. We can take the list of API calls, imports, and their specific order within the executable, hash that, and come up with a thing we call an imp hash or import hash. The point being that even if you do this kind of polymorphism to change the file hash, the imp hash will remain the same in our dropped files. So out of curiosity, what kind of imports do we see from our dropped files? I took a look at one of the files in PE Studio, which lists the imports. We see that there are 108 imports, and I highlighted one of them here, write file. Since we see write file, we can make a pretty good guess that this malware sample will write another file to disk. And here is another import. We see that this malware sample is importing the connect function from WS232, the WS being WinSock. This tells us that this sample probably makes a network request like a C2 connection, or maybe download yet more files or exfil stuff. If you don't know what the connect function does, you'd search for it in your favorite search engine and find the Microsoft documentation. This code is from the Microsoft documentation showing how you would use connect. To sum it up, we saw the sample had 108 imported functions, which should be a large enough sample size to give us a useful imp hash value. On the other hand, think of a sample that has no inputs at all. That's going to result in many, many false positives. If you ever want to have a laugh, create a file with 0 size, take a hash of it, and look that up on VirusTotal. Check the community section. You'll see people claiming it's all kinds of different malware. And in this sample, we saw that there were 4 DLLs imported. kernel 32, user 32, WS2 32, comctl 32. I'm not an expert here, but the imports that were interesting to me were these: connect, write file, load library. So we can guess that this malware sample will write a file to disk, maybe run a DLL, and maybe create a network connection. So back to the dropped files and the polymorphism. How do we find out what's different in the 4 files? Remember that our array that had the 999, 999 values? We can look for the values before or after the random values. In my case, I searched for the 7 bytes before the random values, which you can see in the last line of the slide. In each of the files, this set of values occurred only once and at the same address, followed by 4 bytes, which were made up of values between 2 and 8. Remember, the 9 values are extremely rare, 1 in 10 million. We didn't get any 9s. So the next cool thing to do would be to determine where in the code the random values exist. Like, did they exist in fields that just aren't used, or are they in some other way in some function area that is not used at all or just ignored? But I didn't do that. I'm not knowledgeable enough on PE file structure to pursue that. So back to our VBS. There were still a lot more functions that we haven't looked at yet. So what else does this dropper do? Turns out there are 17 blocks of obfuscated code in addition to the encoded file that was dropped. We expect most of those blocks to be additional functions. So let's take a look at the second block. Turns out that this block is a function that does some WMI to get the size of the disk. See the yellow highlighted things. Select star from Win32 logical disk. So we want to find out the size of the hard drive. Why would the threat actors want to do that? The second highlighted thing gives us a clue. The threat actors want to know if the hard drive is under 50 gigabytes in size. I'm guessing that the FSFCH means something like file system check. So if we fail this check, meaning the hard drive is smaller than 50 gigabytes, we log a false message and then we run LDJ. Well, what is LDJ? Let's take a look. Time for another sidebar. What is LDJ? Note that LDJ is just another one of the obfuscated code blocks. In the red highlighted thing, the threat actor is testing if the file name of the VBS is the string 82984. If so, we log sandbox push and end the function. If not, we run more stuff. We run function DLA, blah, blah, blah. We run function Nimbus, and then we do wscript.quit, which ends the execution of the whole VBS. Now I kind of want to know what DLA and Nimbus do. DLA is yet another obfuscated function, and here's the code. Note the thing highlighted in green. This function wants us to do some kind of HTTP request. Then we take a look at the yellow highlighted stuff. We pass in some value to the function, and we see that the passed in thing is part of the GET request. And then there's a send call. So whatever is passed into this function, that's where we send the GET request, meaning we're expecting an FQDN or IP address. Let's flip back to the previous slide. What were we passing in? So this HTTP request is not going to work in that the GET request is sending to dash. So theoretically, this function may be to reach out to C2 like a beacon, but it appears that this feature just isn't used. So let's take a look at Nimbus. Nimbus is a very simple script, just these 2 lines. All this does is delete a file. In this case, wscript.script full name, which means delete the VBS that is running. So this appears to be the threat actors cleaning up after themselves. they are destroying the evidence that is the VBS file. So if our hard drive is under 50 gigabytes, we send a HTTP GET to nowhere. We delete the VBS file and we end the script. So seems like they're cleaning up after themselves, just destroying evidence. So one more thing, why 50 gigabytes? Had a hunch and started creating a new VM in VirtualBox. By default, a Win10 64-bit VM defaults to a 50 gigabyte disk. When you calculate it the way the VBS does, the result comes in slightly smaller than 50 gigabytes. So a default Win10 64-bit VM in VirtualBox would be too small for the VBS to run. As I guess to why the threat actors would do this, this is just anti-analysis, as in, if you're running this VBS in a small VM, you're probably doing malware analysis. You're probably not a real user at a real host. So we're not going to show you what the VBS does. And I'm guessing that we don't want to go through each function. We don't want to go through all 17 one at a time. So here's a summary of what the other functions do. And we can take a look at just the interesting stuff. We see other anti-analysis things like checking for number of cores. If under 3, quit, destroy evidence. If physical memory is under 1030 megabytes, quit and destroy evidence. The functions on this page that I found interesting are function num, which the threat actor is labeled fs process. This does some checking on running processes. Other interesting one is function era, which is labeled frun. This is the thing that actually runs the dropped DLL. And our list of functions continues. We have other functions that do various things, and the interesting ones from here are the ones highlighted in green. I liked fmessage and flockfile. So let's take a look at the interesting ones. In fmessage, we see that the threat actors pop up a message box with that specific error message highlighted in yellow, the can't start msvcr101.dll. And here's what that error message looks like. And my guess is that this is a false flag. They're trying to convince the victim that the VBS ran into some error. It didn't really do anything, so just go on with your life. However, that msvcr101.dll, I guess that file doesn't actually exist. I did a search for it, and the first hit is Trend Micro, identifying that as part of a malware sample. The next couple of hits show that msvcr110 is a legit file name. I don't know if this is just a typo by the threat actors or they intentionally used a fake file name. My point here being that the fake error message kind of backfires on the threat actors. They want the victim to think that nothing actually ran, but if the victim searches for that file name, they will find something suspicious, right? So let's move on and take a look at flockfile. So in this code, what we're doing is if a file named adobe.url already exists, this is the thing in yellow. If it already exists, run ldj, which is the thing that deletes the VBS and ends the process. Otherwise, we go to the green highlighted section. Else, we create the adobe.url file, which only contains a hyperlink to adobe.com. So one thing you may be asking is, well, what is Sandhill? Sandhill is yet another function that was obfuscated. And all this does is return the environment variable temp. And below the dotted line is what it looked like on my VM. So since we haven't seen anything malicious in this flock file, I actually tried it. It's exactly what you'd expect. It's a shortcut that only contains a hyperlink to adobe.com. There's nothing malicious about it at all. So why would the threat actors be doing this check? My guess is that they're using the adobe.url file as a mutex, meaning if the adobe.url file already exists, this host was already a victim of the attack. So there's no need to run the VBS again. And here's another interesting check, FS process. This actually does 2 checks. The yellow highlight shows that the script queries all running processes. The green highlighted thing steps through the list of running processes, and if any of the running processes matches the name in a list in the script, we quit and destroy evidence. The orange highlight counts the number of running processes. If there are less than 28, quit and destroy evidence. So what's in the list? Sorry, I know this is really small to read, and even then I couldn't fit all 139 items. But in this list, we do see a lot of malware analysis things like Procmon, Process Explorer, Ali Debug, WinDebug, TCP dump. And probably our most important function, frun. This is the thing that runs the dropped file. The key thing is highlighted in yellow, where we see run DLL32 is used to run ratio.drc. Ratio.drc is the file that is dropped earlier, the one that has the 4 randomized values in it. In green, we see the functions that we saw before in HTTP get request to nowhere, and Nimbus, which deletes the VBS. And I snipped this part out of frun in the previous slide to make it more readable, but this is pretty interesting too. Remember earlier, there was a function that checked if the VBS file was named 82984. We see that if statement again. This time, if it's the testing file name, rather than run the dropped file with run DLL32, we're just running calc.exe. So if you've ever heard the term popcalc, this is what they mean. You run calc.exe to test that the thing you're trying to do works. So remember back at the beginning, the Xavier Mertens article was named Russian doll something something. Well, that was a pretty good description in that there are layers to this malware, right? The innermost doll would be the payload, the DLL that gets dropped. Then there is a VBS script which obfuscates the DLL payload, making it unreadable without processing. Then there is another layer of obfuscation where we take each function from the VBS, we obfuscate that into an array of integer values. Okay, so it's time to start wrapping this up. As a malware analyst, my job is to relay some information to some other teams that need it. First, I need to get information to my incident response team as quickly as possible so they can contain the attack. I want to report back to my incident response people that if the VBS ran on the victim host, we should find some new files, the ratio.drc file, and which is the DLL that was dropped for the VBS, and the adobe.url file, which is totally benign, but they appear to be using it as a mutex. I also want my incident response people to look for the run DLL32 process, which executes ratio.drc. And finally, remember that error message MSVCR 101. We can ask victim users if they saw that error message. I also want to get information to my threat detection team. This would be the people who create methods to detect malicious activity. First, we have a couple of ideas from the run DLL32 execution. Should we be seeing run DLL32 execute a file with a .drc extension? In general, this should just be files with a DLL extension, right? Next, should we be using run DLL32 to execute files from temp? Shouldn't your DLLs be in a system folder like Windows System 32? Next, we'd like to review the process ancestry. A VBS file will probably be executed by WScript or CScript. Should WScript or CScript be running run DLL32? I don't actually know how common this is. I'm guessing or hoping not very common. I also have a threat intel team that wants information on tactics, techniques, and procedures, TTPs. So I'll want to provide them with some highlights using the attack techniques. Under execution, we have user execution, the VBS file that needs to be run. It could be that the VBS file was actually a macro in a Microsoft Office file, in which case the victim thought that they were just opening a doc or a spreadsheet. We also have Visual Basic, which should be kind of obvious in that it's a VBS file. And we have a bunch of WMI queries, which were used to gather information on the victim host. It appears these queries were used to determine if the victim host was a real victim or a malware analysis sandbox. There were also techniques that fit under defense evasion. There were execution guardrails. Remember the specific file name that the threat actors used for testing. If the VBS file was named 82984, then don't run DLL, just pop calc. We also have the adobe.url mutex. If the mutex is already there, don't run the DLL. And of course, the WMI stuff we mentioned just a few slides ago. If it looks like an analysis sandbox, don't run the DLL. We also see signed binary proxy execution, in that the threat actors are using totally legit run DLL 32 to execute ratio.drc. And that's the end of my presentation. The rest of the slides are just references. I'll be over in the chat to answer any questions you have. And if you have any other feedback, please do let me know. Thank you very much. That's all I have today.